So, two things we're going to do: square root property and completing the square. Quadratic equations is where we're going to be spending the vast majority of our time for the next several weeks. Lots and lots and lots and lots of quadratics. We've been dealing mostly with getting quadratics in standard form. Standard form is what we use when we want to use our zero factor property. Okay? Remind me how we solve using our zero factor property.
Add one over there.
Okay. We want our equation set equal to 0. And then what?
And then you multiply the 1.
Uh-huh.
And then you find the factors of 2 that add to give you negative 3 and multiply it 2.
Mm-hmm.
So that would be
Negative 1 and negative 2.
2. Yeah. Sorry. And then you factorize your thing. And then
I made that a 3 for some reason. There we go.
you get a 2x.
There
And then you get x minus 1. And then you get negative 1 and then x minus 1.
So it's the same thing we've been doing?
Not at all. It's like
This is what we've been doing so far.
Do you have any tissue?
I do not.
Can I go get some?
Hurry up. You're going to leave your bag here? Plan on going somewhere?
Huh?
Leave your bag here? You plan on
I
going?
always have my stuff.
It'll be safe here. Alright, so I factored it. Now what? Set them both to 0. Okay, so that's what we've been doing. We've been solving for x. Okay, when we get an equation, but we can only do that if it's factorable. Okay, if we have a quadratic that's not factorable, then we can't use our zero factor property. Okay, so another thing that we're going to talk about is our square root property. So, our square root property, we're looking at when I have a quadratic, but specifically I've only got one instance of the variable, meaning I don't have a linear term. Okay? I've got my variable, it's squared, I got a bunch of other stuff, but you don't see x in there anywhere else. We can isolate the x and then square root both sides in order to solve for x. When I square root both sides, that cancels out the x, and that leaves me with a positive square root and a negative square root. Note the difference between when we had our radical expressions, and I had our principal square root, and we had negative square root. These radicals were in the problem to begin with. So that's how we pick whether it's positive or negative. But if you start with something squared or raised to any even power, and you're the one doing the rooting, you're adding it in as an inverse operation, then we have to remember that there are two solutions, one positive, one negative. So when we look at an example, okay, real simple to start. Not even using square root property, just using inspection and thinking about it, what values could I have for m that when I square it gives me 64? 8 and negative 8, right? So I could have m equal 8, which would be 8 squared equals 64. I could also have m equal negative 8 to still give me 64. That's why if we use the square root property, when I square root m squared, I get m. When I square root 64, I get positive and negative 8. I have to include both because I have two possible values of m that make that statement true. Okay? Two values of m that make that statement true. Positive 8 and negative 8. You can write it either way, plus or minus 8, or as 8 comma negative 8. Either one's fine. Alright? I do plus or minus because it's less one. So that's kind of what that square root property is. Now in order to do the square root property, my variable has to be by itself. The x squared. Whatever's being squared has to be by itself. So how can I get my squared factor isolated? Okay, so we're going to add 54, divide by 3, and then we can go ahead and square root. Now, 54 divided by 3, can I actually do that division? Say again. 18. Okay, so we're going to square root both sides. X is going to be positive and negative square root of 18. 18 is not a perfect square, but does it have a factor that is? So I can simplify this. 9 and 2. What's the square root of 9? 3. So I have positive and negative 3 square root of 2. Again, that's two answers. I have 3 square root of 2, and I have negative 3 square root of 2. Three square root of 2. Alright. So, quick, easy word problem. We got an expert marksman holding a silver dollar forehead level. Drop it, draw his gun, shoot it as it passes his waist level. If the coin falls about 4 feet, using that formula, find the time that elapses between the dropping of the coin and when it was shot. Okay? So, where am I going to put this 4 feet into that formula? What do you think T stands for? Into the D. What do you think D stands for? Distance. Distance, distance. Fill it in. 4 equals 16 T squared. Now let's solve for T. What do we think T represents? Okay, solve. What do? Get T squared by itself. Divide by? No. 16. Divide by 16. Okay. 4 over 16 simplifies to what? 1 over 4. Okay. Now what? Square root both sides. Square root both sides. What's the square root of 1/4? Close. The 1/2 part is right. What's the square root of 1? What am I missing? Nope. Plus and minus. Okay. Now, I've got time equals either negative half a second or time equals positive half a second. It's an application problem, so we have to pick which one makes the most sense. Positive one. Okay. So that's our singular answer. The other one is extraneous. Does not apply in this context. All right.
Wait, okay, again, apart from when you got T equals plus or minus.
So remember, this is two answers: a positive 1/2 and a negative 1/2. So I just wrote them separately, and then we're finding the time that it took for the coin to fall. Can't have negative time. Now, what's being squared for this example is already isolated. So it's going to be a little bit different than the earlier example in the fact that I can go ahead and do my square root property now, because there's nothing else over here. Okay? So we apply our square root property, and I end up with 3x plus 1 equals positive and negative square root of 2. Square root property gets rid of the square. Then I have positive and negative square root of 2. Now, still need to get x by itself. So there's two options. You can leave it plus and minus. This is what I'm going to do. If that gets overwhelming, you can always write it as two separate equations. You can write as 3x plus 1 equals the square root of 2, or 3x plus 1 equals negative square root of 2. And then just solve them both. Okay? I'm going to stick with the plus and minus just because it's less work. I don't want to write the equation out twice. The same result. In the same form. So now we get x by itself. Doing what? Minus 1. Now watch how I write this. Because I like my radicals at the end. Okay? So instead of writing minus 1, I'm going to write a negative 1. And then plus or minus the square root of 2. Okay? Negative 1 plus or minus the square root of 2. Last thing to do? Divide by 3. I'm just going to divide the whole thing by 3. So x equals negative 1 plus or minus square root of 2 over 3. Now that's 2 answers. Okay? That's 2 separate answers. Negative 1 plus the square root of 2. Bless you. And negative 1 minus the square root of 2. It's 2 separate answers. X equals both of those. Nope. Now, the next thing we're going to do is going to be completing the square. I'm not going to read the next slide because you can read it later. One, we'll walk you through step by step. Completing the square, I think it's fun, but I'm a weirdo. It is very formulaic, though. Okay? Every time I come back and I teach completing the square, I have to think about it for a second the first time. Okay? I look at the notes, I review it, I work it out again. Because it's not something that just immediately, boom, I've got it every time. It's been years since I've done it. But the formula is so consistent that I'm able to recall it repeatedly year after year with relatively little effort. So I don't expect completing the square to be something that, boom, you work through it, you're done. But as you practice it more, you're going to get more and more comfortable with it. Now, completing the square is something that we use when we're working with application problems with quadratics. When we have situations that are modeled by quadratic equations, completing the square allows us to get very important information that we can't get by factoring or by using square root property. Okay? So, completing the square takes a quadratic equation and gets it into vertex form. Vertex form of a quadratic is along the lines of, there's little variations with it, but it's along the lines of this. Okay? That's our vertex form. What we're doing when we're completing the square is we are forcing our quadratic equation in standard form to become a perfect square trinomial. Perfect square trinomials always factor to a binomial square. Okay? Perfect square trinomials always factor to a binomial square, so we're going to force it to be that way. There are a couple variations on how to complete the square. It mostly varies on what you do with the constant term. So I'm going to do it one way. I have a method for my madness. There's a reason I'm doing it that way. If you happen to look up on your own how to complete the square, it might look a little bit different. The main difference being what is done with the constant term. Okay? So, first thing we need to check is, do I have a leading coefficient? If I do, I can do something with it first. If I don't, I can continue. Do I have a leading coefficient? No, it's 1. Okay? That makes our job easier. It's easier to complete the squares. All right? So, again, remember our goal is to force a perfect square trinomial. A squared plus or minus 2ab plus b squared. Meaning the first and the last terms have to be perfect squares. Is that a perfect square? Is that a perfect square? No. That's why I had to complete the square. Okay? The reason we want a perfect square trinomial is because they always factor to a binomial square. That's what gets us into the vertex form. Okay? So what we're going to do is we're going to separate the first two terms from the last term. And those spaces are there for a reason. We're going to separate the first two terms from the last term. And this, in parentheses, is what we're going to turn into our perfect square trinomial. So I need to add a perfect square value there in that box. Okay? I need a perfect square to be in this square. All right? But it can't just be any perfect square. It has to be one where if I square root it and I double it, I get 2. Okay? So that it fits this pattern. So there's another formula we use to figure out what number goes here. Okay? This derives from our quadratic formula, b over 2 squared.
Will these formulas be given?
Mr. Harris?
Yeah.
Did we do this last year at algebra too?
We did. Okay? B over 2 squared. What's my b value?
2.
Negative 2. That negative is important. Okay? So, negative 2 over 2 squared. Simplify that fraction. What's negative 2 divided by 2? Negative 1. Now, we're going to come back to this negative 1. It's very important. But when I square negative 1, what do I end up with? 1. So that's the number that goes in here. But I can't just add 1 to my equation willy-nilly. Right? Because then that's the equation, and then I'm not going to get the right answer for x. So whatever I add to complete the square, I will also subtract to keep it even. Whatever I add to complete the square, I'm also going to subtract to keep it even. All right, so I added 1, but I also subtracted 1. So everything's still the same, but now I have a perfect square trinomial. And a perfect square trinomial always factors to a binomial square. Okay? Now, that negative 1 that we started out with, this right here, before I square it, goes right here.
Before you square it?
Yep. Minus 1. What's the square root of x squared? Binomial squared. It's a perfect square trinomial. I know it is because I forced it to be one. And then I can factor it using the same pattern as a perfect square trinomial. The square root of the first term, the square root of the last term. If I multiply and doubled it, I get the middle term. Okay, so that's that pattern for a perfect square trinomial. So I forced that to happen. And then I can just simplify everything on the outside. Negative 10 minus 1. Negative 11. This is our vertex form. Vertex form. Okay? Vertex form will become very, very useful later. That's why I'm doing it this specific way, because I want to continue to have vertex form, because we're going to use it. The other way for factoring requires an extra step to get into vertex form. We're just going to do an extra step. Okay? So I've got my equation. Okay? That's the converting, so that's completing the square. Complete the square. Now that it's been completed, now it's a perfect square trinomial. Now I can factor it using my square root property. Get your square term by itself, square root, continue to solve for x. So what's the first thing I need to do to this equation to get my squared factor by itself?
Do x squared minus.
No, I don't want to back up. I want to solve for x. So with the 11, add 11 to the other side. Take that 11, move it over. Add 11. We want to get the squared term by itself before I square root anything. I can't square root if I still have the 11 there. Or you can, but it's going to be really hard to actually find the root. You need to have that isolated. Okay? Now, I can square root. So when I square root both sides, what am I going to end up with? X minus 1 equals plus or minus square root of 11. Okay, remember I got the plus and the minus, both. I have to keep both. All right, and then last step. By doing what? Adding 1. So 1 plus or minus square root of 11. Again, two answers. It's 1 plus square root of 11 and 1 minus square root of 11. You can leave it as plus minus, that's fine. I don't care. That represents both. So now I solve for x.
That's the answer?
That's the answer. The square? That's the easiest way to complete the square. Is there an easier way to get to x? Yes. But I need you to know complete the square for stuff we're doing here. Alright? Do it again. No leading coefficient, so that makes my job easier. Alright? So I'm going to split the first two terms from the last one. X squared plus 3x plus something minus 1, and then I'm going to subtract the same thing. So whatever I put in that square, I'm going to add it and subtract it. What's my formula that tells me what I can put in that square? B divided by 2 squared. What's my b value? 3 over 2 squared. All right? That's already simplified as much as it can be. Don't write as a decimal. It makes it more annoying than it's worth. Leave it as a fraction. Okay? So 3 over 2, that's the number that I'm going to end up inside my binomial squared when I factor it. Okay? But I still need a square to put it in those boxes. So what is 3 over 2 squared? 9 over 4. Okay? So 9 over 4 goes here and here. All right, 9 over 4 goes there. All right? So now I can go to my factoring. Square root of x squared, square root of 9 over 4, 3 over 4. Square root of 3 over 2. X square root of x squared, x, square root of 9 over 4, 3 over 2. That's that same number we had here before we squared it. Quantity squared. Perfect square trinomial into a binomial square. Now we just need to simplify what's on the right. Negative 1 minus 9/4. Yeah, you need common factors, subtract fractions. So minus 13 over 4 equals 0. So now we've completed the square. We've got our quadratic formula, or our quadratic equation in vertex form. Okay? So now we can solve. Get our binomial by itself, so we're going to move the 13 over 4 to the other side. So we add 13 over 4. Then I'm going to square root. Square root, x plus 3 over 2, I don't know why the x is that small, equals positive and negative, square root of 13 over 4. I can simplify that radical. 13 over 2. Remember, our product rule says if I have a fraction inside a radical, I can do the radical to both the numerator and the denominator separately. 13, I can't simplify as the radical, but 4, I can. Square root of 4 is 2. Okay? This is the reason why you want to leave these as fractions, is because simplifying square roots with decimals is don't use fractions. Okay? Most of the time, we also end up with common denominators, which makes our life a whole lot easier anyway. Okay? So I've got my radical simplified, so get x by itself by doing what? Subtract 3 over 2. Where am I going to put that negative 3 over 2? Right in front. Negative 3 over 2 plus or minus root 13 over 2. You can leave it like that, or you can combine it over one fraction, since they both have a denominator of 2. Either way is fine. I don't care which one you use. There'll be an exception when we have complex numbers. But for that, it's real. Either one's fine.
So it has to be in that order.
Radicals, it's just the nomenclature. Putting a radical in the front, having plus or minus root 13 minus 3 just looks awful.
Where'd you take off?
So write it like that. I might take off 1 point. You can in about 15 minutes. Alright, I'm actually going to do one more example. Because this last one is going to be a doozy. This is going to cover kind of everything. This is like the ultimate, like most complexity that you're going to see. Okay? Because I have a leading coefficient, which requires something. I've also got, I'm going to have an imaginary solution, which is going to require something different. And we're going to have a radical in our denominator, which is going to require us to rationalize. Yeah, it's going to be fun. All right, I need to get rid of that 5. I need my leading coefficient to be 1. So I'm going to factor it out. But I'm only going to factor it out of those 2 terms. Okay? I'm going to do a magic trick. It makes it easier. Because I don't want to do 12 divided by 5. That's annoying. Okay? So I'm just going to factor it out of the first 2 terms. 5 x squared. If I factor 5 out of my second term, what do I get? Negative 3x. And then I'm still doing this right here. Okay? That. And I've still got plus 12. And then I'm going to subtract whatever goes in that square, except, here's the trick. Because I factored out a 5 here, whatever I put in here is actually 5 times more than that number. So in order to keep it balanced, whatever I put in here, I need to multiply by 5 over here. That's how we can keep it balanced. So I don't have to factor out anything here, but I still have to keep it balanced by multiplying by 5. Because if I distributed this 5 back in, whatever I have in this box is 5 times more, so I need that box to be 5 times more as well.
Did you just do 12?
If you want to do the fraction, that's fine, but I like doing this. Now I can look at completing the square. So what's my b value? Negative 3. Okay? So negative 3 over 2, that's what's going to be in my factored binomial. I need to square it to put it in there. So what am I putting in there? 9 over 4. Okay? Let's go to factor. So leading coefficient stays there, the 5 that I factored out. It still comes along. Then I have x minus 3 over 2 squared. That's the factoring. That went there. And then 5 times 9 over 4. 45 over 4. So let's take this and simplify it. Positive 12 minus 45 over 4. Just 12 over 1. Common denominator. Okay, so I have plus 3 over 4. So now I have it in vertex form. Continue to solve like we've been doing. I'm going to write a little bit smaller because I'm going to run out of room if I don't. 5x minus 3 over 2 squared equals negative 3 over 4. So I subtract. Now it's negative. So since I have that negative, I know I'm going to end up with an imaginary number. When I square root it, I'm going to have a negative in my radical. But I still need to finish getting my squared factor by itself. So what do I have to do next? Divide by 5. So I divide by 5, which is the same thing as multiplying by 1/5. X minus 3 halves squared equals negative 3 over 20. Am I good to square root now? Yep. Square root. Now we see that where that imaginary number comes from. X minus 3 halves, I don't need the parentheses anymore, equals positive negative square root. We'll simplify that radical at the end. Let's go ahead and get x by itself all the way. Last step. Add 3 over 2. 3 over 2 plus and minus square root of negative 3. Okay, so now I've solved for x. I just need to simplify my answer. There's two things wrong with it. One, I've got a negative inside the radical, so I need to take care of that using I. Secondly, I'm going to have a radical in my denominator, which I cannot have in the end. So we need to rationalize. Okay? So that's where this process comes in. Alright? So how do I simplify and deal with the fact that I have that negative? 2 plus or minus I root 3 over root 20. Now I have that 20, I can simplify that. Root 5. I root 3 over 5. Okay, now I got to get rid of that square root of 5. So this is the rationalizing. I'm going to multiply. Why do I always do that? Okay. I'm not allowed to keep a radical in the denominator. So what I'm going to do is I'm going to multiply the top and the bottom of that fraction by that radical. What's the square root of 5 times the square root of 5? The square root of 25. Which is 5. That's how you rationalize. You multiply the radical by itself, which makes it a perfect square, which allows you to then completely root it, getting rid of it. Okay? So this ends up being 3/2 plus or minus, before I simplify, the root of 15 over 2 root 25, which becomes 5. What's 2 times 5? 10. That is the pinnacle of complicated. Won't get any worse than that. That just includes all the possible things that you'll see. That leading coefficient, an imaginary number, having to rationalize. Get over it. Welcome to school, where there's work to be done. I rewrote it as a 5. What's the square root of 25? Can you simplify square root of 50? Questions?
Oh, no. Not for the
Okay. Because I had 2 times the square root of 25, right? So when I simplified the square root of 25 to 5, I still have to do 2 times 5 to get 10.
You did not the answer. Right? That's the answer.
Okay. It is. It is.
How many questions are
87. No, you get 20 minutes. Yeah, for real. Why not?